Hello? Okay. Hi. Welcome to Erlang Factory. So the disclaimer I'll start off with before we get going here is the actual name of this talk is Vector Clocks in Coq, an experience report. But Garrett Smith, who I'm sure you're all familiar with, arranges somehow consistently with program committees to get all of my talk titles changed to An Unexpected Journey. Specifically because I've not seen The Hobbit nor read The Hobbit, and yeah, he's got this joke which I think is pretty funny that all technology that I use somehow I get this unexpected journey and I never know what is going to happen. So I'm going to just keep riffing with it. So yeah, so the talk is called Vector Clocks and Coq Experience Report. I'm a software engineer at Basho Technologies. Excuse me, that was loud, where I primarily work on multi-data center replication. In addition to that, I do some graduate work when I have time, which is few and far between these days. And this is kind of just a project that I've been exploring on my own because I think it's interesting. So it doesn't really, it's not super practical. It's just an interesting approach to looking at how to potentially solve a problem that may or may not be interesting to you. So the general outline of the talk, we're just going to walk through the introduction. We'll do a little background on what Coq is, what core Erlang is, the extraction mechanism that we use to generate the code, which is not written by me, which is written by somebody else. And then we'll talk about how we can actually use that utility and build some adapter, like glue layer between it, so we actually can use the generated code inside of the React database, obviously, that Basho makes. We'll look at the evaluation, how it performs, what the challenges were, and then we'll kind of talk about what I think are the next steps that I'm going to continue researching towards furthering the idea of like verifying models and properties of things and using them in a production system. Okay, so what are the goals of the project? The goals of the project are very different. We'll talk about the very specific goals of the project, but the goals of the project are very, very different than the goals of the actual talk. I'm going to gloss over a bunch of stuff. I'm not going to show a lot of the core Erlang code, just obviously because like if I put a slide up for 10 seconds, you're not going to be able to digest it. So there is an open source repo with all of the code. I've written a series of blog posts that actually walk through it. So those will be a little bit more technical version of the talk that I'm going to give today. And then we'll look at the contributions of what the repo provides. There's also a paper that's been written that outlines a lot of the work, a lot more detailed than this talk. And what the things that were out of scope for this project were and how it relates to other stuff that's related, other stuff that I also have repos for that you can go investigate if you're interested in pursuing this further. And I'm happy to talk about it too, because I think it's a really interesting idea. So what are the goals of the project? So at Recon West, I gave a talk about distributed data structures. So how many people here are familiar with CRDTs? Okay, a few. So CRDTs are basically data structures. It's a way to build these data structures that build off of bounded joint semilattices. And they have a very nice useful property for distributed systems where operations on those data structures, because of the lattice properties they observe, can be associative, commutative, and idempotent. So it allows for batches of events to be reordered. It allows individual events to be reordered. And it also allows to replay the same event multiple times. So we like these things because we can get determinism in an otherwise non-deterministic distributed system. So there's been a bunch of work. Basho is involved in doing a lot of research on CRDTs. I think there was maybe a talk at Erlang Factory last year about it. There was one at Recon. There's some other talks that people have given at other conferences around here about CRDTs and how you use them. And what I sought out to do as part of coursework when I was at Brown University was finding a way to formally specify the CRDTs in the proof assistant and then prove some trivial properties about them and explore how we might be able to use that in further work. Since then, some people at Kaiserslautern have been working on this as well. And in addition to that, some of the people at INRIA have also been working on it. So they've taken it much further than I did, and they have a lot of work based on how to, they also have some talks coming up at a conference in April about how to specify these things. So this is the original motivation of the work, is how can we write these data structures and use them in React, but formally prove some properties about them. And it'd be nice to have it so we don't have to like formally prove some properties about it and then write it in Erlang and then also like test every possible combination of like interleavings of operations on those events or things like that. So the general idea is we want to explore the applicability of extracting code from Coq. So the proof assistant itself has the ability, it has its own dependently typed functional programming language. It also has the ability to take the code that you write and extract that code out into either OCaml, Haskell, or Scheme, and we're going to talk about core Erlang, which is what somebody has an experimental project that allows them to do. And the whole goal is to, to provide this alternative to rigorous testing, right? Like the way we go about certifying these things now is we write a quick check model and we have people double check it and triple check the quick check model, and then we run the quick check model forever, like 3 days or something crazy like that. And it'd be nice to not have to do that, or to provide an alternative to exploring ways to do that. And a big problem is that we're developers who are writing these. What we do is we take an academic paper that comes off the shelf, that's like, here's how you write data version vectors or something, and the paper defines a series of lemmas about proper, there's a series of lemmas and a formal specification. And we take that and then we interpret it the best way we can in Erlang, and then we write a quick check model. And the problem is that, that translation is not always correct. And you run into situations where you're like, hey, the quick check model says everything's fine. I thought I asserted these properties that I read and I consumed from the paper. And then you find a flaw in the quick check model, right? Like from a trivial use case where something breaks, and then you're kind of like, OK, I have to go back and reassess. Did I even write the quick check model correctly? So it's this classic problem of how do you take like this very formal model of something, and then how do you look at the actual implementation of it and make sure that that implementation is correct. So what are the goals of the actual talk? So we'll provide a brief introduction to Coq, a brief introduction to core Erlang. We'll talk about what vector clocks are. If you haven't heard Basho talk about that enough. And we'll provide an overall experience report of the entire process. Cool. So what are the contributions? So we have a Coq model providing an implementation of vector clocks or version vectors, depending on how you use them. We have extracted a core Erlang module that is generated from this code using the extraction tool that we'll talk about. We have a glue module that's used to basically do type conversions and a bunch of other environment things. We'll get into the specifics that we have to deal with there about how to get the boundaries to work when we cross those boundaries. There's a detailed experience report that's written up in a paper. And then there's an extension to Rebar that's been open source that allows for compilation of core Erlang. So that's a very general thing that you could use if you're writing core Erlang in your project. So what's out of scope for the work? So verification of the actual model. We're not going to talk about any of the lemmas that we could prove about the vector clock model. It's actually pretty trivial. I have another repo that has a more efficient implementation that has a bunch of properties proven. That's not the focus of this work. And one of the reasons it's not the focus is because we're exploring the applicability of the code generation aspect and not writing the theorems. That's like not really appropriate for the conference, as well as the way the proof assistant, the way you prove a lot of these properties through induction and stuff like that in the proof assistant are tied very closely to the way the data structures are modeled. And during this work, I had to basically, it was originally implemented on top of finite maps, then finite sets. Then it was implemented on like a normal like inductive list and all of these things. So I kept changing the data structures, and every time I change it, all of the proofs would break. So that's not the focus of this work. Also efficiency. The code generation doesn't generate really efficient stuff. The stuff that we fight with practically, in our everyday work. The proof assistant is going to generate a code and say I should use an or dict rather than a dict because of like time and space efficiencies. It's not going to look at any of that stuff. So we're also not going to talk about efficiency. We're going to look at a very, very simple implementation, very simple, because it will be easier to consume as listeners of the talk. So we'll talk about the background. So Coq is an interactive theorem prover, if you haven't seen it before. It has like 3 kind of languages in it. It's got a vernacular for dealing with stuff. It's got a dependently typed programming language inside of it called Galena. You basically, write a series of functions and definitions and properties about things, and then you can go and prove properties about those things through like destructuring and induction and all stuff like this. And it can do some automated stuff, but not as much as others. And in terms of code extraction, it has the ability to extract code to scheme, Haskell, and OCaml. It's actually written in OCaml, so the OCaml code that gets generated is probably the most functional code. We do have some stuff that we played around with doing with Haskell code extraction in relation to vector clocks as well. And finally, core Erlang is an experimental module that has been written by somebody named Tim Karstens, who built it as it appears to be as a school project, but it doesn't really say, and it's not really maintained that much anymore. But it does have a bunch of examples with things like interval hash trees and stuff that have been implemented in the proof assistant, extracted out into an Erlang module that you can run. So we'll walk through a brief example of what this stuff kind of looks like. We'll do a couple slides, so when you actually start to see the code that we wrote, it'll make a little bit more sense. So if you're familiar with type systems or type languages, here's an inductive data type called nat, which models piano numbers. So you have two constructors, and you have the O constructor, which is the base case, and then you have the S constructor, which takes a nat and returns a nat. There's some formatting stuff that was left out of here because I copied and pasted it and it didn't work out well in LaTeX, but I apologize for that. So that's pretty straightforward. You have two ways to construct natural numbers. So like a 3 would be the successor applied to the base case a number of times, and that's how you build up your number types. So obviously naturals, 0 and greater. And then if we want to implement, again, sorry about the formatting, and then if we want to implement BLE nat, which is a Boolean function that returns a Boolean that computes if a number is less than or equal to another. Basically, there's a function signature. It's going to take n and m of type nat, return type bool. Then we basically just do some simple pattern matching. This should be familiar to Erlangers or anybody who's done like Haskell or OCaml, where we just pattern match and then destruct on the pattern there. So you have we're going to match n with the base case. It's true, s of n, and then o and false and things like that. So cool. So a core Erlang, how many people here are familiar with core Erlang or have worked with it? Okay, so a few more people. So core Erlang is an intermediate representation for Erlang. There's a bunch of papers about it. If Costas is in the crowd, he'll probably have something to say about that. It's designed for programmatic manipulation of code. So it's designed for tools to basically be able to compile the core Erlang and programmatically manipulate it and rewrite part of the program. So it has a very, very simple grammar. It's very, very desugared, and we'll see an example of this. So a lot of the guards are not enforced as guards. It's all boiled down to case statements, basically. And here are the two functions that you would use if you're actually inside of an Erlang shell. You can do C, module name, to core, or from core. So you can basically, and this from core is actually going to look for a file with .core as the extension. A rather unfortunate file extension, if you ask me, if you're a Unix programmer. But so this will look for a .core file and then try to compile it. And all of this support we added to rebar, so you can basically have a source directory with .erl and .core files, and it will build them and compile it all and package it up. So that's good, and that's how we provide a version of rebar in this vvclocks package. Which implements this that you can just put into a project. So we just were able to add it as a dependency of React, compile React using the new rebar, and build all of the core files and have it all work. So here's an example of the extracted code. So this is not very idiomatic at all. But here's the same function we looked at, the less than or equal to. And we're modeling, it's important to know here that we're modeling the constructors as tuples. So we have an atom, the atom O represents the base case, and then we have the atom S with N inside of a tuple, and that represents the successor case. So you can imagine that this becomes a nested tuple of a nested tuple of a nested tuple, and that would represent the number 5. And this is the core idea of how this extraction program basically does the mapping between the two. Because you don't have this type system, you don't have this ability to do these abstract data types. So you basically encode constructor calls. So the first part of the tuple, if it takes more than one argument, it has a tuple, and it uses the first position of the tuple to represent the actual constructor name, and then it has the rest of the arguments to the function. Cool. So Erlang, or Erlang, I don't know how you would pronounce that verbally, is an experimental extraction module for Coq that will generate core Erlang code. And the way that this does, so this is the project written by Tim Carsons. It's open source on GitHub. So the way it works is that when you go to do the extraction itself uses an intermediary language called mini-ML, which is a desugared subset of ML. And then that goes to either Haskell or Camel or Scheme. And what this does is it basically provides a mapping from mini-ML to core Erlang. And it's got a number of caveats, because you can imagine we're going from a very typed language to a language that's dynamically typed. So there's a bunch of challenges about how you map that stuff together. So let's look at what these caveats are. So the first one is the lack of module nesting. So Coq, when you actually are programming in it, you have the ability to do nested modules as far as you want, and you can namespace things and call things. Core Erlang doesn't really support this. Really, there have been some attempts, obviously. Core Erlang does not support this at all. Modules have one name, and it's just like it's an atom. So we don't really have the ability to do this module nesting. So we have to kind of munge the namespace a little bit, and the way we do this is through taking the full namespace name and basically using like a quoted atom with a fully qualified path, which obviously starts to make things a little bit more complicated. There's no currying, right? So in Erlang, you don't have currying like you have in like Haskell or Camel. You can kind of do it manually in the same way you could do it in like JavaScript, but you don't have, there's no like real partial application, right? So this is problematic when using higher order functions, like things like folds and filters and things like that. And we'll see an example of, I have a slide where I show code that the extraction is completely wrong, because what we want to do is we partially apply a function and pass it around. But that's not possible, so what it essentially does is convert that to a function that takes, rather than have it return a function, it basically creates a function that takes 2 arguments, and then the code fails to execute at runtime because it has no way of catching it at compile time. The other difference is intra versus inter-module calls. So core Erlang has a way to distinguish intra versus inter-module calls through call versus apply. We don't have that concept here, especially because of the weird way namespacing happens. So you can easily work around this by just fully qualifying all the calls and treating every call as an inter-module call. Finally, there's no receive primitive, right? Like the proof assistant does not, unless you encode all the Erlang semantics, which there are projects that have attempted to do this as well. You have no concept of what a receive is, what a process is, things like that. So without this receive primitive, it limits a lot of what you can do, and we'll see. I don't actually have an example on this slide for that, but I do have some examples of that as well. So we'll do the vector clocks review. We'll keep it quick. So what are vector clocks? So vector clocks are a method for reasoning about events in a distributed system. It allows you to identify causal dependencies or causality violations or things that are actually events that are really concurrent. And the way that it does this is you basically pass around a vector of these clocks. And these clocks basically have an actor identifier of somebody that's performing an action, and then it has an identifier of how many times they've performed an action. And sometimes you have timestamps. We talk about the challenges of introducing timestamps for pruning because vector clocks can get very big when you have unbounded actors. And if you're familiar with how databases kind of track causality between versions in the database, that's commonly referred to as a version vector. Structurally, the objects are exactly the same, but they have different semantics about how they're actually used. Similarly, if you look at in the CRDT literature, there's a type of CRDT that's called a G counter, which is a counter that grows only. And that is associative commutative idempotent, and so it converges to the correct value regardless of the ordering of events. And what that does is track how many times. The G counter is actually interesting because it does not have idempotent updates. But there are other counters that do. But it basically tracks it in the same way that you would a vector clock, just the number of operations performed by actors. And that's stored as basically a list of, if you want to think about it in terms of Erlang, that's going to be stored as a list of 2 tuples. and the two tuples will basically be the actor identifier and then the count. And if you look at, we actually model as 3 tuples because we put a timestamp in for pruning, but if you look at vclock.url in React, we have a full implementation of vector clocks with the EQC tests and everything, so you can go and play around with that if you'd like. We also have a dot aversion vector and a dot aversion vector as well. Okay, so implementation. So we'll talk about the vector clocks, then we'll look at the code extraction, and then finally we'll look at the adapter layer. So what do we want to do? So we want to provide an API that's compatible with React Core. So we want to provide the exact same API that vclock.url in React Core uses, so we can basically transparently swap out our module with the module that we generate, the React module with the object that we generate. And here's a sampling of the API functions that we need to provide over vector clock. So we have a way to generate a vector clock through fresh. We have an increment call, an equality check, a descendant check, which is a descendant of, it determines if the second argument is a descendant of the first. It's not, there's a strict descendants as well, which would check both ways. And then there's a domination function as well. Merge function to take 2 vector clocks and combine them. A get counter, which basically says, give me an actor, given an actor, I'll tell you what the counter is currently at. Given an actor, I can tell you what the timestamp's at with get timestamp. A method to return all of the nodes that exist, all of the nodes that have been involved in updates on that vector clock. And then a mechanism to prune the vector clock. So based on a given timestamp or a series of given timestamps, I know how to remove certain entries from that vector clock. And that's primarily used in the event where an actor has gone away or something like that, right? So what does this look like in the proof assistant? So to simplify things for the purpose of this, we're going to model everything as natural numbers. So we're going to treat the actors as natural numbers for the point of this. We're going to define the count as a natural number, which makes sense, right? You start at 0, you count upwards based on operations. We're going to treat timestamps as natural numbers. So the proof assistant doesn't have a concept of what a Unix timestamp is or a timestamp or things like that, right? So what we're going to do is we're going to make an assumption that Unix timestamps do monotonically increase and clocks don't roll backwards, which is not true in the real world, as we've all seen, but we're going to make that assumption for the purpose of this work. And then we're going to define an individual clock as the product of an actor with the product of a count and a timestamp. So what does that really look like? It's basically a 3-tuple, right? It's a product of these 3. So the actor, the count, and the timestamp, so 3 natural numbers. And then we're going to define a vector clock, so we're going to create a new type called vclock, and we're going to define it as a list of the clocks. It's pretty straightforward, and the list is inductively based on a nil and a con, so if you've ever done like a list and scheme or closure, or you've ever read the SICP, you know this like concept of like nil and cons. And here we say fresh returns the type vclock with the nil constructor, so a list. So what does the increment function look like? So to increment, we want to basically provide an actor, and then we want to provide a vector clock. And this is where things start to get hairy. So ignore the repetition. We'll talk about that in a second. But what we want to do is we want to find the actor in the vclock if it exists. And if we do, so this returns an option type. So we either get none or some with the value. And this is us destructing it. So what we basically do is, if it's not there, we create a new one. So we create the pair of the actor, and then we call this init count method and this init timestamp method. So the init count gives us the initial count to start at, and this is so it's provide a lightweight abstraction so we can just call to get the increment count or to get the initial count, because later we have to replace those functions. We'll talk about why. And then we create the new one, we cons it onto the list. In the event that it's already there, we get the existing one out. We increment the counter using the incrCount function. We increment the timestamp using the increment time function. And then we basically just add it to the list with the one removed. So obviously not written for efficiency, but written for clarity. So it's interesting why we have to do this init count and init timestamp and incrCount and incrTimestamp, right? So in the proof assistant, what does it mean to increment a count and a timestamp? Well, those are natural numbers, and they're modeled as piano numbers, so we apply the successor function to those numbers to get the new one. However, in the actual database, we're not going to just increment the timestamp by 1, right? So what do we have to do there? So actually, when we perform the code extraction, we have to provide a bunch of functions that we replace at extraction time to say, well, the increment timestamp function really just gets the current time and puts it in. So these functions serve as placeholders that allow us to reason about things in the proof assistant, but then when we actually go to do the extraction, we have to swap those functions out with real functions. So this is the starting point where things start to break down when we start thinking about like the real system, where a lot of these things have to happen and like use real data like from the environment or from the time, the clock, and things like that. So things start to get more complicated. Additionally, we'll see that this function here, so this is a find, this is a higher order function that takes a function and it takes a clock and it's applied against vClock. And we pass in this function here. So we basically say, you're going to give me a clock, destructure it, and then perform the equality. So see if the numbers match. That's how we know we have the matched actor. Now, this function has to be, so what I'd really like to do, and what we did in the initial version is we say, well, I just, this matcher here, I can just call this matcher like whatever, actor equals or something. I can create a function, right, for it. The problem is this has to close over actor here. So I need to partially apply it. And if I partially apply it, when I go to actually do the extraction, it generates Erlang code that doesn't work. So we have to duplicate this function a lot of places. So this is a bug. This is a bug that I'm working on fixing. But it's another place where we have this impedance mismatch between the two. So if we look at merge, merge is basically the same thing. You see the repetition of the equals here. You see the repetition of the filter where we remove the actor. So this is the max function. And this is the merge function. So what's the merge? So to merge two vector clocks, what we're going to do is fold over the vector clocks, use one as the base and the other one, match the actors, and then just perform a pairwise maximum over the elements. It's pretty straightforward. Function here is basically the same thing. We perform the same pattern. We got to search through the list, find the actor, extract the actor out, and find the actual increment, do it for the second one, perform the max function against the two. So you'll see the application of that here. We say, get the max of the counters and get the max of the timestamp, merge them, and then just recons the list back together. So it's actually really straightforward. But again, you see a lot of repetition. So this is like, unfortunately, this is like this is not the best way to do this, right? So in the original CRDT work that I was working on, in that one, we use like a set or something where we can perform a find on it, or we use a map or something like that. That's a lot more efficient, obviously. The problem is that code really fails to extract because it uses, it has to support a ton, has to use the extraction of a ton of supporting libraries. So it has to take all these core libraries in the proof assistant and convert them as well because you have dependencies on all these core libraries. Pruning is interesting as well. So pruning is a fixed point. So this is just a recursive function that takes a vClock and then it takes timestamps. So this is actually a typo. This should say timestamp here. But timestamp and nat are the same type, so it does work. Small, large, young, and old. So we'll see why this is problematic shortly. But again, you have the same pattern here. We have to destructure the things, just apply lengths, and we destructure on the vClock as a list. You have a nil constructor, and you have a const constructor, which I've left off, but it's basically very similar. Same with descends as well, similar pattern. We do a fold again. This one we actually use a descends helper because we don't need to close over one of the values, and we explicitly just pass in. So we pass in two vector clocks, and then we just compute based on the pairs, whether one is a descendant or the other. So with the core Erlang code extraction, the three main problems that we deal with immediately, which are bugs in the extraction procedure, are missed data constructors, so missing data constructors. So the constructor, like when you construct like a nil type, it just basically doesn't extract it at all. So we have to manually write these. And at the time of extraction, we have to insert that code back in. We also deal with incorrectly qualified calls. So because of this module nesting and everything wants to be an intermodule call, sometimes calls get misqualified with an additional namespace. So we also need to have a procedure to go through and prune out the namespaces that are redundant. And again, lack of currying, which we briefly talked about and we'll see an example of in 2 slides. Lack of currying proves a problem with any function that you want to repeat that you want to partially apply. So missing data constructors. So here's the missing data constructor for fresh that didn't get exported because it was the nil type. So we basically just manually write some core Erlang. Not very complicated, should be pretty straightforward. Fresh is the name of the function. It's of EraDS 0. It's a function that returns an empty list. When dealing with incorrectly qualified calls, we have a problem where, so we see the duplication of vclock here. So the actual file is vvclock, lowercase letters, vvclock.v. And there's a module called vvclock inside of it because it has a bunch of other supporting stuff in there that I'm not showing. So some of these calls get incorrectly qualified. So here we see we're calling that natural number inequality function. And this is the call, so this is calling with the arguments of actor and a, which obviously have been left off. So what we need to do is go through and prune this part out here. So just cut this out and leave just the vvclock BLE_nat. And that would be the module function arguments. So familiar. We also deal with functions with missing EraDS as well. So here's a call to a function. It wants to call this descends function, this descends helper, no EraD on it. So obviously that fails. That does not actually fail to compile. That actually fails at runtime. It does not detect that at compile time, which is unfortunate to debug. Yeah, a lot of this is really unfortunate to debug when you actually have to see it work. Lack of currying. So here's an example. So here's our function as we defined it in Coq. So it's a find function that takes an actor, and it returns a function that takes a clock. And so this is the helper for the find function that basically takes a clock, returns type clock, and it matches and just says, hey, did the one, does the actor match? Is this clock actually the one I'm looking for or not? So it's just a simple test function, simple predicate. And here we see that the code that it generates in core Erlang isn't exactly correct because it's returning a function that takes 2 arguments. So that doesn't really work when we attempt to call it with only 1 later on. So this is why we have to inline this call everywhere. So we'll talk about the adapter layer. So in terms of the adapter layer, there's a bunch of things that we have to address. So the first one is we saw the things. Oh my goodness, what did I do? I don't know how computers work. So the adapter layer, the first thing that we have to address is type conversions, right? So we've already seen how we have to model everything as tuples, and these tuples have to be nested with the constructors. So those types obviously don't exist in Erlang at all. So we have to provide a conversion mechanism to go between the 2 types. Also, we'll see that Boolean is problematic, right? Boolean is a data type with 2 constructors, true and false. And you match on the constructors. That doesn't exactly work in Erlang, right? Because in Erlang, true is an atom of true, and there's one occurrence of that atom, right? Same in false is obviously the same way, so we have to provide conversion between those 2. Timestamps, so we've modeled them as piano numbers, so we need to actually provide glue code to convert that to the actual native data type for modeling timestamps. And we do that with Unix-style timestamps, so the Gregorian conversion. Actors as well, so actors in React in the vclock model can be any term. So we need to provide a way to convert terms to natural numbers, which is problematic, and we won't get into that, but we'll briefly touch on it. Oops. And environment variables are another problem. How do we deal with things that the proof assistant doesn't know how to get things out of the Erlang environment, doesn't know how to do an application get env call, right? Again, API normalization is another problem because some of the functions that have been exported out to that core Erlang module might not necessarily match the actual calling conventions that we want in vclock. So we actually have to do a little bit of tweaking to make that work as well. And finally, we have these weird circular dependencies that we have where I say, somebody calls into the vector clock function and says, I want to increment. We call into our verified one and say, increment this guy. That has to call back out to get the timestamp and has to return back in to do the timestamp and do the conversion. So that's also interesting and not necessarily wonderful. So with the type conversions, we'll briefly look. This is obviously the most inefficient but easiest enough to reason about in the on the screen way to convert a natural to a piano. So basically, right, if we have 0, we pattern match. We have 0, we return O. If not, we return S, and we recursively call. So obviously, that could be way better if it was a tail call, but whatever. Same to go back, piano to natural, whatever, works. Type conversions, here's the example of Boolean. So our equal function in our vector clock adapter that takes the 2 vclocks calls into the verified version and calls equality on it. And then we match on the atom capital true, which is the true constructor for the Boolean type in the Bool library. And then descends, same thing, right? So we have to do that same conversion again. In relation to timestamps, so with timestamps, we call calendar date time to Gregorian seconds, Erlang universal time to generate a timestamp, and then we have piano timestamp, which basically takes that timestamp, converts it to a piano number, and that's the caller for the verified version to get the timestamp to use when it goes to make the vector clock. So with actors, so actors are interesting. So with actors, you could define a way to, convert some sort of Erlang term uniquely to a number or hash it to a number somehow. But it needs to be two-way, right? So you can't use something like a SHA-1 because you have to be able to go back and say, hey, the verified version gave me this thing, I need to convert it back. So there's a bunch of ways that you can do this, but it's slow, right? Because those numbers are not going to be small. They're going to be big, especially if you need them to be unique across all Erlang terms. So you could instead model the data type in Coq as a string. So what is a string? A string is the empty string, so it's just like a list, right? It's a basic cons. It's an empty string, and then you have a string that takes a string of ASCII and an existing string and returns a string. And this is the definition of the base type of a string. So what's a string? So what's an ASCII? An ASCII is a series of bits that could be false or true. So inductive writing the conversion for this obviously is slow as well. It's not as slow, but it's really slow, regardless. So it's interesting how you want to deal with that as well. So one thing that we explored was saying, well, maybe we don't prove anything about the actors at all. We just use things that stand in for it. And because the actors are not really the important part here. What we want to verify are things like the pruning function and the merge function to make sure that they're always deterministic. So here's the prune function. So the prune function in React takes 3 arguments. It takes a vector clock, a timestamp, and it takes bucket properties. So yeah, Coq doesn't know anything about React. It definitely doesn't know anything about bucket properties. I barely know anything about bucket properties, and I work at Basho. So we can't pass that stuff to the prune function. So what we have to do is we have to write the verified prune function. This is why I showed it earlier, taking the 4 timestamps. It takes the vector clock. It takes the small timestamp. It takes the large. It takes the young. It takes the old. So it has to take all of the arguments. It needs to have all of the arguments formal, right? And then what we can do is we can prove that that prune function is always going to prune correctly, right? That it's always going to prune, younger than the greater than the whatever it is, younger than the oldest, greater than the youngest, greater than the smallest, smaller than the largest, or whatever. So we can ensure all of that stuff. So we have to write this wrapper code here, right? So this get property is something that goes to React, gets the bucket properties, it examines the bucket properties, pulls out these atoms out of the bucket properties, then performs the conversion. So there's a bunch of adapter stuff like this where we didn't think about functions that explicitly go and talk to the environment, which you actually have to do in real systems. Normalizing the API, little stuff like that. You see that, again, for the type conversion on the increment, we take the actor and the vclock, and we basically have to do the piano term conversion stuff on the actor, and we have to make sure that when we get it back, we convert it the opposite way. With the merge function, this is how it's actually, these are the 3 types of case clauses that the actual one from Erlang has. So what, we wrote a we wrote a pairwise merge, which is easier to prove things about. So what we need to do is apply that to a list. And again, with the circular dependencies, here's an example of, this is the generated core Erlang code, and this is the actual, so this is the vclock.url, so this is our adapter, and this is the vclock.core. So what we do is, in the increment, we call into the increment, but the increment needs to either generate a new timestamp or know how to update the timestamp, which we've said that in the real world, we just want to get the current time. So what we do is we have to, in the core Erlang, we have to do that extraction time substitution where we say, really call back into vclock and get the timestamp. And this would normally be the successor in the actual extracted version because that's how we defined it in the original implementation. So what's the evaluation look like here? So the test suite passes, which is pretty cool. Took a lot of work to get there. There's lots of little weird things we have to do. It runs really slowly, hence the performance problems, right? The data structures are implemented really inefficiently. It'd be nice to use some of the more advanced data structures, but use the faster data structures or the more compact representation data structures in the proof assistant. You don't necessarily guarantee that the extracted code matches that at all. You could use the most efficient implementation in the proof assistant and get out like the worst core Erlang code possible. Obviously, it doesn't know anything about Erlang, so it doesn't know how to compile code that's relatively performs well or anything like that. And obviously, a lot of the other performance penalties come from the overhead that's required from doing all of the coercion between types and all of these conversions to go from naturals to piano and terms to things and integers to things and atoms to things. So a lot of that's slow and cumbersome and not necessarily great in a system where you want things to be super fast, like our database. Finally, there's this idea of testability, right? So now I've wrote this thing and I've formally proven that my merge function will never, it will never merge incorrectly. There'll never be a missing value. That's great, right? The problem is that I wrote this whole adapter layer that has to do all this type conversion, and that's not tested at all. And that's where a lot of the problems were, obviously. So that's also an interesting thing. Obviously, quick check helps here. That's where I initially went to say, well, can I quick check all of these functions that basically do all of these conversions and verify things went well? And for the most part, it does work, but it's not necessarily great. So what are we thinking about for future work? So obviously, fixing all of the bugs that we discovered and manually patched around through like scripts that would either fix code or apply things. Obviously, all of those bugs that we found in the extraction utility itself, I will be working on fixing and pushing that forward so people will not have to deal with that stuff in the future. We really want to explore other applications. CRDTs were the initial version CRDTs were the initial version of this work, the G counter. I simplified it to vector clocks because the G counter and vector clocks were very similar, but people had were more familiar with vector clocks, and because I had a nice testing platform that I could actually run my code inside of React and it would work. So that was nice. But what we really want to do is when we start building these more and more complex CRDTs that are composed and nested and span multiple keys and that allow us to do transactions over, when we start building these more and more complicated data structures, we want a way other than like writing a quick check test that could possibly be flawed, which have real world experience with dealing. But ultimately, we're not at that point yet. As you've seen, this is the point of the talk. Again, the adapter layer is just terrible for performance and testability. It adds a bunch of additional work. It makes you really start questioning why you did the initial work in the first place for something that's not super complex. But it's an interesting experience of realizing what it takes to encode a language with types inside of a language that does not have types or the same type of types. Haha. And finally, the work that I'm exploring now, which I think is more interesting, is saying, well, rather than looking at the ability to generate Erlang code from the formal specification, why don't we try generating quick check models? So an alternative approach would be, I can prove all these properties about some things. So I can basically take a paper and say, hey, there's this lemma, and I'm going to put this thing in here. I'm going to prove these properties about it using the exact same proof that's in the paper, prove it in here, and have that automatically generate a quick check model to guide my implementation of the code as I write it in Erlang in the most efficient manner as well. Which seems like it might be a more practical approach. Obviously, quick check gets complicated fast if you built anything that's sufficiently involved. So that's an interesting further work. And that's about it. Thanks.
Great.
Good?
Do we have any questions?
Yes?
So you're currently manually generating partially applied functions in the adapter layer?
No.
It's spitting them out automatically using something.
In what regards? The partial application with the currying?
Right.
No, what we're doing is just manually inlining all those calls in the actual calc code, so then it doesn't actually generate. It actually generates correct.
Right.
It's just it's a matter of just the way you write it and how the extraction process works. It's basically just a bug in the extraction that doesn't understand how to properly extract those functions.
Do we have any other questions?
I'm curious, how involved would it be to introduce processes and messages and multiple nodes, and even if you just introduce that to the quick check properties, what do you think along those lines?
So there's a really interesting work that somebody did in, I think it was China, as part of their master's thesis, where they wanted to, they were working on, I forget what it was some database or something. They were working on some academic database project that they wanted, that they were involved in. And they wanted to basically find a way to prove properties about an algorithm that was used in the database. And what they did was they encoded a bunch of properties about how Erlang message passing works at like a very high level. So a very common way to formalize it is like as a series of functions that take like step relations, like a bunch of processes are basically functions that step to new state over time. So they model it like that, and they have a whole paper that talks about how to verify the algorithm. I think that's one of the major only other works about like trying to, so they're doing the inverse, right? They're trying to encode. They're not trying to write like a very simple data structure and export it. They're trying to take all of the Erlang semantics and put it inside of the proof assistant so they actually can reason about it. I don't know how far they got. I read part of the paper when I started doing this work initially, but I did not finish it, to be honest. Just so many other papers to read.
How hard do you think it would be to prove Dynamo in this?
I have no clue. I could not speculate. What would you prove about Dynamo? I mean, yeah, that's an interesting question, right? If you want to prove the eventual consistency model, there's actually an Erlang factory talk from 2009, 2010, John Meredith's.
Well, that was quick check.
Yeah. So I mean, yeah, to do it formally, yeah, I don't know. I have no clue. There's a bunch of papers on formally proving properties about eventually consistent systems, and like. People like Peter Alvaro and Peter Bayless and stuff have worked on similar stuff, but yeah, I have no clue offhand.
Great. Any other questions? Thanks a lot, Chris. It was great.
Thanks.